الآن يمكنكم المشاركة في مبادرة الأيام الرقمية تحت شعار انطلق بقوة مع جوجل، والتي يتناول فيها خبراء جوجل عناوين جديدة أسبوعيا مثل السحابيات، مهارات من جوجل، أندرويد، فلتر، ذكاء الآلة، فايربيس، ديزاين ثينكينج، مقسمة إلى دورات وورشات عمل يومية بالإضافة إلى مسابقات أسبوعية. شاهد الأيام الرقمية مباشرة على اليوتيوب وشارك رأيك وأسئلتك مع خبراء جوجل، واحصل على شهادة حضور في كل محاضرة تشترك فيها. هذا وأكثر من الأحد إلى الخميس ابتداء من الساعة 9 بتوقيت دبي عبر الرابط المبين youtube.com/gdgmina.
Hi, everybody, and welcome back. And so earlier I was talking a little bit about, the state of the art of where we are with TensorFlow today and what we've been working on and some of the new stuff that's there. But for this talk, I want to kind of go back and just go from zero to hero with TensorFlow. So if you're not familiar with AI, if you're not familiar with machine learning, I'm just going to talk about some of the basics of machine learning and how it works, and then how easy some of these things are done with TensorFlow. And I'll focus on computer vision in particular. So first of all, I like to talk about just thinking about what programming actually is when you write code on a computer. And I like to think about it in terms of three different types of artifacts. There's rules, there's data, and there's answers. So for example, if you're writing a function to calculate a PE of a stock, and if you're in finance, the PE of a stock is the price divided by the earnings, and it's a good way of understanding the value of a stock. Well, you got data. So you can read the price from the time series of like what the stock is currently trading for. You've got data for the earnings, and you can just divide the price by the earnings to return a value. So you have rules that you're expressing in code, you have answers that get returned from the code, and you have data that the rules are acting on. Or for example, if you're writing a game, again, you have rules, you have data, and you have answers, right? So rules here could be, if you're writing a breakout type game like this one is, if the ball collides with the brick, then you want to remove the brick and change the trajectory of the ball. So again, these are rules that you're actually writing. There's data, and you're getting answers. In this case, the new trajectory of the ball from the code. So I'll create like a high-level diagram to describe traditional programming, and I kind of like to do it like this. We have a box. We're passing rules and data into the box, and we're getting answers out. This is the simplest diagram that I could think of to describe really what programming is. And the rules part of it is what we kind of make our money on, what our career is all about, is figuring out how to express rules in code. If this, then that, while this, all of those kind of things. Machine learning, the idea with that is that we just turn the axes around a little bit. And the entire revolution of machine learning and what machine learning is all about is just that. So if you look at the bottom diagram, instead of rules and data in and answers out, it's answers and data in and rules out. And you might think, okay, what's the point of this? Why is this so powerful? How do I put answers and data in and get rules out? I don't understand, and I don't blame you. And so let me explain this with an example. A very common device now we wear on our wrists. I have an Apple Watch here. Many of us wear these kind of devices, maybe a Fitbit or something like that. And one of the useful things about this is to help us with fitness. And then as a result, it needs some kind of activity detection. It needs to know if we're walking or running or biking or those kind of things. But how would you write code for that? Now, typically, you might write code to say, okay, well, if my speed is less than a certain amount, I'll set my status to walking. There's my rule, right? If the speed is less than an amount, my data is I'm measuring like an accelerometer to get my speed, say it's 4 miles an hour, and my answer is my status is walking. And say, okay, I have my rules, I have my data, I have my answer. And then, okay, running, if I want to detect that too, and I'll say, well, if it's less than 4, I'm probably walking. Otherwise, I'd say I'm running. I say, okay, it's a rough algorithm, but it kind of works. And then I'll say, what if I want to add biking to that? And I'll say, well, I can continue my if rule, right? If it's less than 4, I'm probably walking. If it's less than 12, I'm probably running. Otherwise, let's just say I'm biking. So I have these 3 activities that I can detect by writing rules. But then I want to do golf. How do I do that? How can I detect that if I'm actually writing, and I'm not riding a bike or walking or running, but I'm actually playing golf? How would I create rules for that? It's not really feasible for me to do that. The amount of code that I would have to write to detect the swing of the arm and followed by walking, or what it looks like when I'm putting, or all of those kind of things, it just would not be feasible for me to do so. So let's go back and look at this diagram for a second and say, well, can I apply machine learning to this where instead of me trying to figure out the rules, because the rules are just too difficult to figure out, what if I figure out the answers and data and then somehow have a computer figure out what the rules are? And that might look a little bit like this, where, okay, I get a lot of people to go walking, running, biking, and playing golf, and I gather data from all of the sensors on the device, like the heart rate, the telemetry, the speed, all of these kind of things. And I start spotting patterns. For example, like if this pattern is in the data, the person is always walking. And if this pattern is in the data, like the 4 ones here, then they're running. If that pattern's in the data, they're biking. And if that pattern's in the data, they're always golfing. And I say, when I've got all of this data, if I can reliably match patterns of data to this thing that I'm calling a label, then I can say that, I now have an algorithm that will allow me to detect if they're walking, biking, running, or golfing. And all I need to do now is figure out how to match those patterns. And that's what machine learning is. So the idea behind machine learning and the paradigm of machine learning is like, let's just make a guess. Let's make a guess that this pattern means walking, this pattern means biking, this pattern means running, that kind of thing. And then let's measure the accuracy of that guess. So I've got lots of samples of walking, biking, running, and golfing, and I guess that this part of the pattern determines them. And I'll measure the accuracy of that and say there's 4 different activities, walking, biking, running, and golfing. The odds are that I'll get it right 1/4 of the time, right? If I just do a random guess. So I can measure my accuracy of my guess. But then what if I could optimize my guess to say, okay, based on this guess, I got pretty close. How can I refine the guess to make it better? And then loop it back and repeat. Make a new guess, measure the accuracy, optimize that guess, and keep going. And that's all the machine learning paradigm is. And TensorFlow is the tools that allow you to do this, and that they do all the fancy mathematics to help you make the guess, measure your accuracy, and optimize that guess. So if I go back to this diagram, like now I have my data, which is my the data that I've gathered from the device, like be it a watch or whatever. I have the labels that I've added to that, which are things like walking, biking, running, or whatever. And with machine learning, it will figure out the rules, and it will figure out the patterns that say, this means when I see this data, they're probably walking. When I see this data, they're probably biking, that kind of thing. And that's the learning phase. And then later, when you create a model out of that, then all you have to do is pass data to it, and it'll give you back what's called an inference. So now if the watch is on somebody or the device is on somebody and they're running, it's generating that data. The model that you've created, which matches data to labels, will say, I see this data, I think you're running. Instead of you writing lots of if-then type rules, it has actually figured out the rules that determine walking, biking, running, or whatever based on that pattern matching. And that's ultimately what machine learning is all about. So let's take a look at what that would now look like in code. And I'm going to do that using computer vision as an example. So how would you use machine learning to understand the contents of an image? That's really what computer vision is all about. So for example, if I give a picture to a computer, it's just a bunch of pixels. It doesn't really know anything about its contents. And to simulate that, I have an image here, and I've kind of blurred it. So if you look at this image, you probably don't know what it is. If you're familiar with image processing and things like Photoshop or Instagram, there's things called filters that you can apply to an image to extract information from that image. With Photoshop, you can, for example, sharpen an image or blur an image, or like add motion or remove blur and those kind of things. And filters are just sets of numbers that get applied to an image to do something to it. But one of the things you can do with filters is actually extract parts of an image. If there's a pattern within that image that repeats, you can use a filter to do that kind of thing. So looking at this blurry image right now, what if I could, for example, apply a filter to the image that does this? Okay, now you detect these two things, and they probably look a little bit like human legs. I say, okay, well, what if there's another filter that I could apply to the image that does this? And they kind of look like human hands. And then there's another one that does this, and this detects what looks like a human face. So now, if I applied these filters to the image, I get legs, and I get hands, and I get a face. And if I've already labeled the image that works with these filters as being a human, then the computer can learn that when it detects these 3 features using filters, what it sees in that image is actually a human. So again, it's the same kind of pattern matching. And maybe similarly, there are other filters to detect things that look like these. And when a computer applies those filters to an image, when the three of them produce something, and that's already labeled as a horse, now the computer can begin to recognize that, oh, when I see, these three filters on the upper one, and they produce something, and they all produce something, and I can see, and there's like something that comes out of that, hey, that's actually a human in the image. And the computer can start understanding that the contents of that image are a human or a horse in this case. So over time, in the same way as we had with activity recognition earlier, the computer could actually figure out which filters extract the features that determine the difference between the answer of a human and the answer of a horse. Again, if we start with a whole bunch of random filters and we make a guess off of those random filters, and we have 1,000 humans and 1,000 horses, and it gets both of them right 500 times each, which you'd expect because there's only two labels. But then we start tweaking with the filters and optimizing them. And then over time, it figures out and learns a set of filters that, hey, if I apply this bunch of filters and I get these set of results, I know I have a human, or I know I have a horse, that kind of thing. So, that's really what the machine learning of these filters is all about. So then in the future, if we pass it a new image that it had never seen before, and depending on which filters actually work with that, they could be combined together so that the computer determines it knows that it's looking at a horse. And this is really the core of computer vision. So now if we go back to the model that I was showing earlier on, we're passing data in, we're getting inferences out. So the data we could pass in here would be this picture. And what does the model do? The model applies all of the filters that it learned to it, and it realizes when it applies these set of three filters here that it gets these things that look like, two like horizontal columns look like human legs, and then maybe two oblong blobs that look like hands, and then maybe a circle with other circles on it that look like a face. And it says, hey, I've applied these three filters, I've gotten these things out. This seems to pattern match what I learned a human looks like, and then it will determine that it's actually looking at a human. So if we go back to the paradigm again, and if you take nothing else away from this talk, think about the paradigm like this. All machine learning is you make a guess, you measure how accurate that guess is, and then you optimize the guess, and then you repeat this again and again and again. So in the case of like doing images with computer vision like this, your guess is you're going to randomly initialize all of your filters, you're going to apply them to images, and you're going to make a guess as to which ones match the labels to the images. Remember, when we're training, I've given it a whole bunch of images to say, this is what a human looks like, this is what a horse looks like, and then it can match based on its filters with the ones that it already knows. Then we can measure the accuracy by matching the images to the labels. Then we can use the data from those previous steps to tweak our filters and then go on and repeat and repeat and repeat. So over time, when it sees something like this, it'll realize that it's a human and that this is the image that was actually underlying it. So what does this look like in code? So here's an example of some TensorFlow code where if this looks a little alien to you, don't worry. This kind of thing will become familiar in time. But the idea is that what we're looking at here is called a sequential at the top. Is like this is defining the layers of a model. And I like to think of a machine learning model as a filter where the data is coming in, the stuff in the filter is figuring out the matching, and the answer is coming out the bottom. So the types of filters that I'm using here are called conv2D. And conv2D stands for convolution, and a convolution is just another word for filter. So when I was talking about filtering images like you do with Photoshop or Instagram or that kind of thing, a convolution is just a filter. Pooling, in this case, is a way of compressing the image while enhancing the features. So if I go back here for a second and say this one, like, okay, I pass my image in, and conv2D, and the number after that is a 16, that's actually going to have 16 filters. So if you imagine if every image is going to be filtered 16 times on this layer, and that's going to produce 16 images. So if I'm now training with, say, 1,000 images, this layer alone is going to produce 16,000 images. So when we look down at the next layer, then there's 32 times that. So our 16,000 images are going to get multiplied by 32. And then our 32 times 16,000 is going to get multiplied by 64 by the time it reaches the third layer. So when I begin with 16,000 images, I'm going to end up with, when I begin with 1,000 images, I'm going to end up with 1,000 times 16 times 32 times 64 images as I go down, which is a lot of images and it's a lot of data. So a trick that you can do is this thing called max pooling in between the layers. And what max pooling does, it's the way of compressing the image. And when I say 2, here, all that's doing is for every 4 pixels in the image, it's picking the biggest value and it's throwing away the other 3. And so it quarters the size of the image, and what that actually does, it still maintains the features that were learned by the filters. So while I'm multiplying my number of filters, I'm also reducing the size of multiplying my number of images, I'm also reducing the size of them, which helps me manage memory a little bit better so that I don't blow up the memory on my machine while I'm trying to train it. And then finally, at the bottom, and there's a dense, and this is the traditional neural network that you've probably seen, where it's like lots of neurons and they're all interconnected with each other. That's what gives it the name dense. So this is often used for matching things to each other. So in this case, I have all of my filters that I've been learning. The image is coming down through the filters. I'm ending up with lots and lots of bits coming out of that. And I now want to match those bits to the labels. And that's what this dense layer is doing. And then this final dense layer is the output. You see there's only one neuron in that. A neuron will have a value between 0 and 1. So it's a nice little trick here because I've only got two classes, horse and human in this case. So I'd say, well, the value of that neuron, let's push it towards 0 if it's a horse, and let's push it towards 1 if it's a human. And the activation sigmoid is what actually does that. So all of the stuff coming down from the upper layer comes down to this one neuron. The one neuron has a function, and from what it sees above, it's going to push a value towards 0 or 1 based on the stuff that's coming into it. And then next is it's called compiling your model. And when you compile your model, you define what's called a loss function and an optimizer. And this is where all of the heavy math takes place in machine learning. And if you've ever started to try to learn machine learning and you see things like a lot of calculus and all that kind of thing, this is where that gets abstracted away from you. So going back to this diagram, make a guess, measure your accuracy, and optimize your guess. Accuracy is done by the loss function. So if you think about the code that I just showed, and I fed 1,000 images into that, and then at the bottom, that neuron with one value is either going to give me a 0 or a 1. What the loss function is going to do is like saying, okay, the model thinks this is a 0. Let me look at the label. It's a 0. The model thinks this is a 1. Let me look at the label. Oh, that one is a 0. I'm doing badly there. And it measures that kind of accuracy for you based on the stuff that you fed into the model, plus the type of loss function that you define. There's a whole bunch of loss functions. In this case, I'm using one called binary cross entropy. The clue is in the word binary. Remember, we just have two classes in this case. And this loss function, binary cross entropy, is really useful when you've only got two classes. So I've just chosen that one. When you look at the TensorFlow documentation, you see there's a whole ton of loss functions that you can use. And a lot of the science of machine learning is picking the right one for the right task. And then the optimizer, the job of the optimizer is just to make the next guess based on your loss function. So remember, we randomly initialized our filters. A loss function then measured how accurate our guess was. Based on the results of the loss function and knowing the values in the filters, then the optimizer will go, okay, I'm going to do the heavy-duty math here, usually something called gradient descent, to try and figure out, based on my loss function and based on my values that I have, how can I tweak those filters to make them better? And that's, in this case, I'm using a called root mean prop that you can see at the top slide. But similar to loss function, there's a whole ton of optimizers, and depending on your model, it's worth like trying a few different ones. And then finally, you're going to fit your model. And when you fit your model, you'll generally say, and again, the clue is in the word fit. Because remember I was saying, well, machine learning is kind of pattern matching. You're fitting the data that you have to the labels that you have. So we call this model.fit. And then you're going to pass it a parameter called epochs. And the epochs is just the number of times that you repeat this loop. So making a guess, measuring your accuracy, optimizing your guess, and repeat. So as you'll see, as you train a model, that's all that's happening there. So let me give a demo to show you what this looks like in code. Let me just give me a moment to share my screen. Oh, my runtime disconnected. I will share that one. Sorry, 1 second. And application. So I'm going to share here. Here we go. So I'm showing here where this is one that I trained earlier on, and this is the code that I showed earlier on, where I've defined this model. I've trained the model, and I want to focus on here where I've trained it. So, sorry, let me just scroll down. My mouse is not behaving. All right, so I'm going to scroll down here and show this model. Let me zoom in so you can see it a little better. So I've taken the horses and humans data. It's about 1,000 images of like combined horses and humans. I've created the model that I was showing in the code, and then I've trained it. So as you look here, you'll see these numbers epochs. So epoch 1 of 30, and then you'll see an accuracy value, right? So you'll see the accuracy value is 0.5732, which is 57%. So what happened there was the model was randomly initialized, and it made a guess, and then it measured that guess. And I got lucky, right? Because it should be 50-50, but I did slightly better than 50-50. It was 57% accurate. So I said, okay, that's pretty good. That's my first epoch I've done that. And the optimizer kicked in and said, okay, I'm going to change the values of these filters to see if we can do any better. And then we're going to pass them through and measure everything again. And then it went up to 76%. So the optimizer did great. Okay, I've done pretty well here. I've changed my guess, and I've moved now from 57% accuracy to 76% accuracy. Cool. So now the third epoch, the optimizer again made tweaked the filters to make another guess, and we measured that, and look what happened. It actually went down to 71%. And then the next time around in the loop, it went down again to 69%. So this is the machine making these guesses and trying to optimize and figure them out. And all it's doing is all of this pattern matching. Now, it might look like, oh, this is going really badly. We started 57, then we got to 76, then down to 71, now down to 69. But we'll see what happens the next time round. It got to 82, and then to 81, and then to 77, and then to 67. So in a lot of these early epochs, the optimizer is just really trying to figure out how to match this data. It's still very much in guesswork, but the overall trend is going up. And that's really, the machine is now learning from its own mistakes in how to match the data of those images to the labels. And when I trained this for 30 epochs, we'll see by the end, I had gotten to 87% accuracy on the data. So we started at 57% accuracy. I ran it just for 30 epochs. It's like 6 seconds per epoch. So this just spent about 3 minutes learning. And it got to be about 87% accurate looking at the data that it was training on and picking the difference between a horse or a human. And I also then gave it what's called a validation data set. And the idea here is like, well, this is how well it does with images that it has seen while it's training. How well or how badly will it do with images that it's never previously seen? And it got to like 76% there, where like you can see 77, 79, 75, that kind of thing. That number will always be lower. But a bad thing that can happen in models when you're training them is called overfitting. And that means the results on the data that it has seen is much better than the results on the data that it hasn't seen. So this model is overfitting a bit here. So a lot of the science of you trying to figure out the best models is to reduce that kind of overfitting. But this is one that I just trained really quickly, like you can see here, for about 3 minutes. I need to work on it to make it, prevent it from overfitting. And if I want to run it and just give an example, so I'm going to run this model, and then I'm going to upload some images to it. And one of the interesting things about this experiment was that the images that I trained it on were computer-generated graphics. I'll show some examples of them in a moment, or they were like the ones that I had on the slide, the very cartoony computer graphics. But when you create filters to extract features from an image, the CGI-based image is still going to have legs or ears or faces or hands in the same way as a real person would have them. And I found that when I train a model off of synthetic CGI images like this, I can actually make it work to mostly recognize actual photos. So these are actual photos that I've uploaded. So for example, this one, white horse, it got wrong. It thought it was a human. This one, horse, it got right. It thought it was a horse. This one, horse, it thought it was a horse. And these three humans, doctor, woman, and confused, it got them all right as humans. But I want to show one of these images. Just give me a moment to find it. And I find this one particularly interesting. I guess I need to share that one. So let me share. I'll share my entire screen this time so we can see. Just make sure it's sharing. So it actually was this image here. And so as you can see, you and I both know it's a woman, but the dress that she's wearing obscures her legs. And I actually thought the image might classify this as a horse. The model might actually classify this as a horse, but it got it right. It determined it as a woman. And if I go back to the one that it got wrong, where's my model here? So you'll see that white horse 640.jpg it thought was a human. So if I go back and I open that image, white horse.jpg, it thought this one was a human. So maybe it's the hair. I don't know. Maybe it's something about the image that it got it. It thought that there was actually a human in this image. So the training data that I was using, remember earlier when I was talking about biases in the training data, that I might need to have more training data of white horses with long blonde hair like this one that are labeled as horses, so that my model wouldn't think something like this is actually a human instead of a horse. And then finally, as we just mentioning, the type of images that I was training on, I use like CGI images like these ones, like to determine this is a human. And one of the things, like all of my humans have their legs visible. As you can see, her legs are visible here, his legs are visible here. But it was still smart enough to learn filters to determine that this actual image, a photographic image of a woman, is actually a human and not a horse. And my training images of horses look like this. I try to be as like diverse in them as possible, different lighting, different poses, all of this kind of thing. But I realized that for some reason, and I need to interpret why, but when I like try to classify this image, it thought this was a human, but it got all of the others right. So that's it. That's everything I wanted to cover. This notebook, this code is available on my GitHub if you want to give it a try for yourself. And I know we need to finish at that point so I can start taking some questions. Should I switch to the YouTube chat room to take questions, Noor? Oh, sorry, I do actually see some questions in the chat. Okay, so I'll take a couple of them. Let's see. So Amine Kirkin asks about Swift, and Swift being the future of TensorFlow in order to have a compiled language as a backbone. I wouldn't really characterize Swift to be the future of TensorFlow, and that was never really the intention. We really wanted Swift to be there as an alternative. We have multiple languages that we support. The data science and the AI community have definitely driven us towards Python, and we can see Python as one of the primary languages that we do. But Swift is still alive and well as far as I'm concerned. We continue to develop it. And so it hasn't been abandoned. There are no other plans like that. We are continuing to support multiple languages. And then you're asking, is JAX going to do that role? JAX is a very research-oriented API if you want to get into cutting-edge research. It hasn't really been fully productized for developers yet, but that's one thing that we are working on, is to see how we can best get the best of JAX available for the general software developer. And I know we're out of time at that point. I'm really sorry. I'm going to drop off, but I'll be in the chat room on the YouTube and I can answer some questions there. So I'll say thank you very much.